In this lesson, we will be talking about variance and bias trade-off in machine learning. First, we will talk about train, test and validation datasets in machine learning and the requirement for dividing the dataset into train, test and validation sets. Then, we will introduce bias and variance and finally conclude with the mathematical definition of bias and variance. To understand the necessity for a train, validation and test set, let's take a small example. Here we have a data set. If we want to fit a model to get a relationship between x and y, the simplest model will be to use a constant. That will be y equals to w0. Y equals to w0 will be a parallel line to the x-axis. This slightly depends on our data set. If we want a better fit, we can increase the degree of the polynomial. So if we use w0 plus w1x, as you can see from the graph, it fits a bit better to our data set. If we increase our model to a second degree polynomial, it closely follows the trend in our data set. Likewise, we can keep increasing the degree of the polynomial. If we use a 10th degree polynomial, it will fit really well to all our observations, including the errors in those observations. In the previous example, I generated the dataset synthetically by adding some random noise to the graphs shown in the dotted line. If we take the 10th degree polynomial, as you can see, it fits really well to the observations. So in that case, if we take the total sum of squared errors, it will be quite close to 0. Though the error is quite small, still we are not getting a better fit to the underlying function, which has been shown in these dotted lines. So if we try to calculate the y value to a given x value, in this example we are trying to find the y value for x equals to 14, it is quite different from the value that actually resides inside the underlying function. To avoid the problem we faced earlier, let's do a slight modification. Let's take the same 10th degree polynomial we used earlier, but this time let's divide the dataset into two parts. Let's call the first part as the training set and the second part as the validation set. When we are fitting the model, let's use those data points in the training set and keep the validation set aside. If we do that, we will get a polynomial function like this. Here we can see it has fit exactly to our training set, but because we kept the validation set aside, it won't fit to those validation points. So there will be a small error between the validation points and the predictions we are getting through our model. In this case, we can define two error terms. The first error term is for the training set, and the second error term is for validation set. Because our function closely fits the training set error will be quite close to 0. But because we are keeping the validation set aside, that error term E2 will be greater than 0. Now we have two data sets to compute the error. Let's start with the most simplest model, y equals to w0, and compute the training error and the validation error. If you do that, you will get a value, just say as an example, 3 for the training error and something quite close to that training error as the validation error as well. Here let's assume it is 3. When we increase the model complexity, the training error will reduce. In this case, if you take the first degree polynomial, the validation error also should decrease because our model fits the dataset a little bit better. If we take the second degree polynomial, the training, we know it is the optimal solution. The training error reduces a lot and validation error also reduced to a quite close value. If we keep increasing the complexity of the model, the training error should keep decreasing, as we know, because it fits to the training data really well. But because we kept the validation dataset aside, that validation error should keep increasing. So we had the optimal fit when we had the second degree polynomial. When we go to the third degree polynomial, the validation error should be higher than that. So for the second degree polynomial we had 0.5 as the validation error, but for the third degree polynomial it has increased to 1.5. Similarly, if we keep increasing the complexity of the model, when we reach a very high value as the degree of x variable, the training error will reduce to a very small value. In this case it is 0.0001, but the validation error will keep growing. In this example it is 10. So when selecting the model we have to look at the validation error. As the optimal model we can select the model where the validation error as small as possible. So in this case when n equals to 2 we have the best solution. But still there is a small problem. Here when we were deciding the degree of the polynomial that we are going to use as the model, we always compare those errors with the validation dataset. So we will encounter a similar problem because here we have effectively fitted the n degree polynomial to the validation dataset. So the degree of the polynomial can fit to our validation dataset. Because of this thing, though we say we get the smallest error for the second degree polynomial, which is 0.5, that error won't represent the true error if we take a totally random new data set. In our polynomial curve fitting example, to select the polynomial we use the validation dataset. So the validation dataset can be regarded as part of the training process. If we want to report the performance of the best model that we have selected, using this validation set won't be that accurate. Due to that reason, it is better if we can have another independent dataset to report the performance of that model. Usually before doing anything with the model, we divide the dataset into three parts. The first part is called the training set, and the second part the validation set, and the last part the test set. The performance of the best model can be reported using that test set. Usually in machine learning we can use about 80% as the training set and 10% as the validation set and the last 10% as the test set. To explain the problem we encountered, there are two mathematical terms. If our model is too simple, it won't fit to the dataset. If that is the case, it is called a high bias problem. So here you can see a high bias problem. If our model is too complex, then it will follow all our observations, including the errors in those observations. If that is the case, it is called a high variance problem. You can see that problem in the second graph. Also, these two scenarios are called underfitting and overfitting. If our model is too simple, it has a high bias and it is called underfitting. If our model is too complex, it has a high variance and it is called overfitting. To understand the bias and the variance mathematically, let's assume we have a large set of samples starting from x0, y0 up to xn, yn. Because this sample is quite large, we can subsample that. Let's assume we have 3 such samples. For each sample, we can fit the model and draw the graph. Because of the errors we have in each sample is different from each other, after we fit the model, we will get 3 curves. Let's assume we have a large set of samples like that. Then we will have y1 equals to f1x, that is the model that we have fitted to the first sample, and y2 equals to f2x, that is the model we have fitted to the second sample up to a very large number. If that is the case, we can define the average prediction as y bar, which is the expected value of all y values. For each x value, let's assume there is a corresponding true y value as yt. This yt is not observable because our observation or the measurement always has errors. Let's assume yi is the function that we have obtained by fitting the sample. So there are samples starting from y1 to yn. Those are our functions. With these definitions, we can define the average error for any given y such that the expected value of yt, that is the true value of y, minus yi, that is the prediction we are getting through the ith function, the squared value of that. Here we take the variation of our functions from the true value. To simplify this, let's substitute the mean of our functions y bar as positive and negative values into our function. After the substitution, we can take the squares of each term inside the brackets. So it reduces to 3 terms. As the expectation of sums is the sum of expectations, we can reduce that further into the form that we have here. Using the properties of the expected function, we can show this third negative term goes to 0. So our variation reduces to the expected value of yt minus y bar squared plus the expected value of y bar minus yi squared. Here yt is the true value of the function, but it is not possible to recover the true value of function because it is the unknown that we are going to find. But we know this true value can be written as a sum of the observation plus small error term delta. Let's assume this delta has a 0 mean and a standard deviation sigma. If we substitute this into our first term here, we get the expected value of y observation minus y bar squared plus 2 into the expected value of delta into y0 minus y bar plus expected value of delta squared. Here the observation y0 and the average of the functions y bar are constants. So the expectation of a constant becomes that constant itself. The term in the middle has the expected value of delta. We assume the mean of delta to be 0. So the second term goes to 0. Also, the standard deviation of the error we assume to be sigma. So the expected value of delta squared should be sigma squared. We can substitute this result to our first equation. If we substitute that there, we get the term which shows us how much our average prediction is different from the observation. That difference is called the bias of our equation. So the first term is the squared value of the bias. This sigma squared is known as the irreducible error. In the final term, we have how much our functions are varying from the mean function. That is known as the variance of our model.